Hey everyone, let's dive right into this explainer and uncover the hidden architecture of the waves that literally surround us every single day. Whether it's the sound of my voice reaching your ears right now, or the light from the sun warming the earth, waves are absolutely fundamental to how energy moves through our universe. So today, we're going to break down the science of mechanical waves. Here is our roadmap for today. We'll be moving through the world of waves, transverse versus longitudinal, the anatomy of a wave, calculating wave speed, and finally, a quick recap and transfer. All right, starting off with section 1, the world of waves. Picture a seagull just bobbing out there on the ocean. The wave moves toward the shore, right? But the water and our seagull mostly just stay in place, bobbing up and down. This is a brilliant example of a core concept. The wave itself is moving forward, but the water actually isn't. The wave is transmitting energy across the ocean, but the physical water molecules essentially stay in their original location. So the crucial takeaway here is that a wave is basically nature's way of restoring balance when something gets pushed out of its resting state. Whenever matter gets disturbed from its normal state of equilibrium, all that energy has to go somewhere. It travels outward as a wave, just like a ripple expanding across a pond when a stone breaks the surface. Moving right along to section 2, transverse versus longitudinal. There is a really cool distinction here. If you're shaking a toy spring up and down, you're making a transverse wave. But if you're speaking, your vocal cords are actually pushing air back and forth to make a longitudinal sound wave. See, in a transverse wave, the disturbance is perpendicular to the direction the energy is flowing. But in a longitudinal wave, the disturbance is parallel, and that creates alternating regions of compressed matter and expanded matter. Okay, time for our first pause check. I want you to take a quick pause, think about how sound travels through the air, and try to answer this question. Keep in mind what we just talked about regarding the parallel movement of longitudinal waves. What is actually happening to those individual air particles? Well, if you guessed simple harmonic motion, you hit the nail on the head. The air molecules just bump into their neighbors and then bounce right back to their original spot. A sound wave pushes atoms together to form regions of high pressure. We call those compressions. And then as the particles swing back, they create areas of lower pressure called rarefactions. That alternating back and forth oscillation, that's simple harmonic motion at work. All right, let's jump into section 3, the anatomy of a wave. What's super interesting about amplitude is that it's completely independent of how fast the wave is moving. It only depends on how much energy the wave is carrying, kind of like the towering height of a massive tsunami. If you picture a perfectly flat, calm surface of water, that's your resting position. The amplitude is just the maximum distance the water gets displaced from that flat line, whether that's upward to the peak or downward to the lowest point. Next up is wavelength. Whether you're measuring the physical distance between two water wave peaks or two sound wave compressions, you are measuring the wavelength. In physics, it's traditionally represented by the Greek letter lambda. You can basically think of it as the physical footprint of one single complete wave cycle before the whole pattern repeats itself. Now, if you're watching waves crash on the beach and you start counting how many hit your feet every single second, well, you're measuring the frequency. Frequency tells us about the rate of events. So when we say a wave has a frequency of 1 hertz, it literally just means one complete wave cycle passes by in exactly 1 second. And then there's the period. While frequency counts the number of waves in 1 second, the period flips that and measures the number of seconds in one single wave. They're essentially two sides of the same coin, giving us slightly different ways to describe the timing of a wave's oscillation. Here's pause check number 2. Pause the explainer again and use those logical deduction skills to figure out how these two properties are connected. Think about it. If the frequency goes way up, what has to happen to the period? It makes total sense when you look at the math, right? If more waves are packing into a single second, each individual wave cycle absolutely must be taking a shorter amount of time to finish. They have an inverse relationship. For example, if 2 waves pass by per second, which is a frequency of 2 hertz, the period of each wave must be exactly 0.5 seconds. Okay, section 4, calculating wave speed. So the big takeaway here is that a wave's velocity is simply how many cycles happen per second multiplied by the physical length of each cycle. In a given medium with constant conditions, wave speed remains constant. Because of that, if the frequency goes up, the wavelength has to get shorter to keep the speed exactly the same. Look at how beautifully simple wave math can be. If a wave has a length of 2 meters and it hits a wall 5 times a second, it has to be traveling at exactly 10 meters per second. You literally just identify your variables, plug them into the velocity formula, where v equals f times lambda, and multiply. It's incredibly elegant how all these properties just lock together perfectly.
And that brings us to section 5, our recap and transfer. Take a quick second to mentally log these core concepts, because they honestly apply to everything from the sound of my voice to the light from the sun. The absolute key takeaways are that mechanical waves transfer energy, not matter. They do this by moving particles perpendicular to the flow, which is transverse, or parallel to it, which is longitudinal. We measure them using amplitude for energy, wavelength for physical distance, frequency for time, and we just multiply those last two together to get the speed. I want to leave you with this really provocative thought. Geologists know for a fact that longitudinal P waves travel much faster through the Earth than transverse S waves. If you're sitting at a seismograph station, how could you use the time difference between their arrivals to determine exactly how far away the earthquake started? Think about how this incredible behavior of waves might actually help us map out unseen forces deep inside our own planet. Keep exploring, and I'll catch you on the next explainer.